Hello, my name is Alec Drosu, and I'm here with Alex, Ari, and Ollie to present our proposal for the Martian Excursion Vehicle. We are group MEEV1, making us the #1 group to give your money to. We propose to have a manned mission to the surface of the Martian moons. Traveling to the moons and understanding the surface could create a bridge between Earth and Mars, preparing for the eventual arrival of more missions to the surface of Mars. This would allow us to understand more of the physical and chemical properties of the planet, as well as some solar effects such as illumination, radiation, and wind. It could also open the door to some energy characteristics, such as perhaps having solar panels on the moon. The more we know about the Martian moons, the more we know about how to colonize it. We already have some pretty big stakeholders in the project, primarily being NASA, JAXA, ESA, as well as some research institutions such as universities and private and public firms, as well as also some aerospace manufacturers. Our objective for this mission is to travel to both moons, Phobos and Deimos, and collect 50 kilograms of samples from each moon. On the moons, we will set up a lander. The crew, after completing the mission, will rendezvous with the main ship to return to Earth. Our main needs for this mission are, of course, astronaut safety, as this will be the first manned mission to not only these moons, but any surface outside of our own moon. Another need is the 50 kilogram samples from each moon, and a rover capable of housing the crew and transporting between the moons. The crew will also be staying for quite a duration on the moons, so the rover needs to be capable of sustained life support systems.
Now that we've gone over the requirements for our design, we need to now go into some of the previous missions that we drew experience from. The two main ones being the Apollo missions, mainly 11 through 17, where we took the inspiration for the landing cradle design. As you know, the lunar lander landed on the surface with a command module being around the orbit of the moon. As the astronauts did their things, they got back in it and they were able to rendezvous with the command module and make their way back to Earth. We did something very similar with our design. The other bit of inspiration we got was from the Curiosity rover, mainly in its data acquisition technology, mainly being that we needed to collect samples into our rover, 50 kilograms worth, so that we can send them back home for study. So now that we've talked about that, let's go a little bit into our ConOps. First of all, the entire system will approach Mars, and when it is there, the crew will decide which of the two moons is best to land on. Once they've established that, they will then plot a course and establish an orbit around said moon. Once that is done, the landing cradle and module will detach itself and it will head toward the surface of the moon. Once that is done, it will depart, it lands with the legs, it will make sure that it lands stationary so that the rover can detach itself and roll out. That is done, the crew inside will gather their 50 kilograms of material with its claw and other data acquisition devices. Once it has obtained its 50 kilograms, it will head back toward the landing cradle, back itself in and redock itself, and the landing cradle will take off from the surface back to the command module, where it will offload its 50 kilograms, recharge its batteries, and refuel its fuel reserves. Once that is done, it will repeat the entire process from 2 to 10, where it will pick out another moon, depart, land, gather material, take back off, redock. Once both have been done and everything has been offloaded onto the command module, the command module will then plot a course, the interplanetary vehicle, so that both the research material as well as the astronauts can safely make it back home to Earth.
Hi everyone. So I'm going to be talking about the system decomposition. So for the functional architecture of our mission, we're going to have the function of landing. And in that, it's important to safely land because, we want to preserve the astronauts' lives. It's important to reliably land as well for their lives, but also for a lot of the equipment on board. You don't want to break any of it. And it's important to have a steady base of whatever excursion vehicle ends up being used, um, can exit safely and without any problems. Next, we have sample collection. So it's important to have a place to store the samples as well as a method of collecting them. Next is taking off. So whatever is used needs to be capable of orbital maneuvers, needs to be able to escape the moon's gravities, which should be really easy, but they also need to escape the gravity well of Mars, and they need to be reliable. Lastly, they need to be able to rendezvous with the main ship. Now, the physical architecture. We have the rover, its life support. Then for the sample collection, we're using a claw. And then the structure, we have the body and the wheels are the two main parts. Now you have the lander, and the lander has propulsion, and then it has its structure and its legs, which are probably one of its most defining features. For the command module, you have life support, propulsion, and structure. It's a little more orthodox in its style. Then we have the N2 diagrams, and here's the interface diagram. And we have our command module leaving the main ship. Then we deploy the vehicle, and then setting up the equipment goes into setting up the lander. And then once the vehicle is deployed, it also collects data, and that leads into the examining data step. Also, we leave the data in the main ship, and then we examine the data at mission control, much like what was done in the Apollo missions with lunar samples. And then, chronologically, then we'll exit the moon and fly back to the ship and then fly to the second moon and continue. So, for the physical diagram, there's the main ship, the command module, the lander, and the rover. Now, the rover exports its data back to the main ship and its feedback, and the main ship exports that to mission control.
Now I'm going to go over the trait studies. And the trait study that we've done to our project was a propulsion type trait study. As a propulsion system, is an essential part and can be a barrier to space exploration. It can be costly and dangerous and hard to maintain. So we've listed 8 types of propellant, starting with the ion and ending with the new that's been NASA been doing a lot of research on, electrically controlled extinguishable solid propellant, which is a solid propellant that has the ability to be throttled. And here we have the weighted values of uh, the aspects that we've listed. And the most important aspects that we cared about are reliability, operational cost, and production cost. And after listing these, and we ended up with the decision that a compressor is the ideal. It's the most reliable. It has the best and operational and production cost. Now I'm going to go over the concept architecture. So we have the key features here. The rover. The rover has the claw that will be able to hold material and put it in the storage. And we have the lander, the command module, the payload storage, and the thrusters. Now I'm going to go over the financial projection. The order should be around $36 billion. Below is each subsystem. So the lander and the command module, the rover. Comparing to other parts of previous missions, our margin or our cost is actually much less. And that will be certainly quite pleasant to the customers who are the stakeholders that they benefit from the mission, understanding better of the Martian system. Lastly, here are our contacts. If you have any questions or concerns, please let us know at this email. Thank you so much.